All right, welcome there, function folks, to the lesson 1.7 on the remainder and factor theorems. We've got a bit of a weird lesson today. The 3-minute review isn't really a 3-minute review. It's more like a 15-minute review. It's like an activity where you fill out a couple of pieces of paper, and this video starts with me taking that up, and it leads into our lesson. So if you don't, it's better this activity to do with a partner. That way you can split up the work. But if you haven't got a partner handy, please get through that sheet, and we'll take it up momentarily here. And then we have the lesson and homework after. And if you don't do this warm up in class or before class, then the lesson won't go very well, and you won't have time in class to finish the homework, and we know that that's trouble if we attack it that way. So do this, and I'm taking it up right now. Okay, so this is the sheet, and the idea is that when we're expanding, we're looking for just the n term, just d. Well, it's going to be just all the terms that have no x's in them. I don't need to expand this entirely. It's just -2 times 3 times -1, just +6, and I can do that the same thing with these other ones, and I get those things. For the remainder theorem investigation, the idea here, it asks you to do two things, which seemed like it was unrelated at the time. They wanted you to just evaluate the value of the function at specific values. For instance, when x is 1, we just put in 1 and we get an answer of 10. But then, on another piece of paper, we did some long division, like we did yesterday. When we divide this into this polynomial, I got a remainder of 10. And we saw that this happened again and again. And that's the pattern, right? And there's the answers. I'm not sure where the questions went. Where are they? Are they behind here? Don't know. Anyway, there's the answers. Not sure where aha! No, this is the second part. You got the answers though. The idea is what we can just do if we want to find out the remainder is we can just substitute into the polynomial, and that's what the remainder theorem says. And it also, in general, if some polynomial px is divided by x minus k, essentially what we do is we substitute in what makes the divisor 0, right? And x equals k would make the divisor 0. And so this expression, p evaluated at k, would give me the remainder. And that was true even for fractional ones. We think about what makes this 0. Well, a half. And if I substitute in a half, I get what the remainder is. Now, what's kind of strange, and hopefully you got that okay, is why do we care about remainders? Well, we'll see soon why we care about remainders, but that leads to, this pattern leads to what's called the remainder theorem. So remainder theorem is actually on page 172, and this in the box is the remainder theorem. If f at x is divided by x minus a, then the remainder is, well, it's f at a, right? We saw that. All we had to do is substitute into the original function the value that makes this bracket 0, and then we get the remainder. We're going to prove this, actually. We've had some feedback from graduates, Husky graduates, and the idea that we don't do enough proofs has led to problems, and it seems like that's where our students struggle, is when their university profs talk about proofs. So here's a proof of this formula. Again, you're not going to be responsible for reproducing this, but it's good to try it, and it's good to see this, because this sort of thing does come up in university where you are responsible for proofs. This statement is a typical math statement, and it says, if blah, that's blah, then blah. And notice that this is different than the proofs that we did in grade 11, right? The Trig Proofs. This has a different form. It says, if this is true, can we show that this is true? So it's kind of like we're given that this is true. So we're given that f at x is divided by x minus a. So that's what we're given, and we're required to prove. We'll know we're finished if we can come up with the remainder is f at a. Okay? And how we're going to start is with this statement. So here we go. Proof. Since f at x is divided by x minus a, what we're going to do is we're going to write our division statement. We can write f at x is equal to x minus a times the quotient, whatever the answer is when we do long division, plus the remainder. And I know my remainder is actually going to be a constant, right? That's going to be a constant because this is degree 1, and we always know the remainder is 1 degree less. So 1 degree less than a linear term is a constant term. So this is just a number, 4 or 3 or negative 12 or 0 or whatever. That's what that's going to be. So now, watch. If I let x equals a, then take out the x, put in an a, take out the x, put in an a, take out an x, put in an a, and then what happens? Well, this is 0, right? So this whole term becomes 0. So what have I got? I've got f at a equals r. And look, f at a is the remainder, and that's what we were required to prove. You put a little square there to show when your proof is done. Not so bad. And again, you don't have to reproduce this. You have to, hopefully you followed along. It wasn't so bad. Similarly, this is another version of a more complicated version of the remainder theorem. If f at x is divided by this factor, the remainder is f at b over a. And if you can't remember whether it's a over b or b over a, we always think about whatever makes this 0, because that's what happened in the proof here. What makes this 0? What makes that 0? Well, it's b over a, and that's how we know what to substitute in. Okay? And that's the remainder theorem, which allows us to do some questions like this one, find the remainder when that is divided by that. And we could have done that yesterday by long division, but basically all we need to do is evaluate the remainder is, if I call this f at x, it's f at, well, what makes this 0? 1/3. Can't see that? Well, think about it in the margin here. What makes that 0? So all I have to do is evaluate this expression at x equals 1/3, and I've got a little bit of fractions going on here, which makes it a little more difficult perhaps, but we're not scared of fractions here. No way. Then I've got 3 over 1 cubed is just 1, 3 cubed is 27, minus 1 squared over 3 squared minus 1/9, minus 12 times 1/3 is 4, plus 7. This is 1/9 and not minus 1/9, so that's 0. This whole thing's 0. Negative 4, plus, that's just 3. And of course, you're quite welcome to jam that into a calculator. I think it's harder to deal with fractions on a calculator unless you got the magic fraction button. And if you got that button on your calculator and you don't know how to use it, ask in class, because it's kind of a neat button. But I think it's easier just to do this fractions in your head. Faster, probably, even. Example 2, find the value of k so that when that expression is divided by x plus 2, the remainder is negative 44. Well, this sort of thing is a typical remainder theorem question. They've got a great example. in the textbook that I want you to read. Again, why do we do this? Why don't I just do the example? Feedback from Husky graduates is that we don't ask you to lean on your textbook enough. In university, you have to learn from reading, and so this is for you to try and do. If you'd like, I can post my solution to this on the Facebook group later. You might need to remind me of that, but learn that one on your own. So these are typical remainder theorem type questions, but really the question is who cares about the remainder theorem? I mean, who cares what the remainder is except for to do these silly homework questions? Well, remember, this whole long division thing came about when we had an expression like this. We wanted to graph it, right? And we could graph it if it was factored, right? And so what's a good remainder to have? We want the remainder to be 0, right? If we could get a remainder of 0, then that expression is a factor, and then we can go on and onwards and upwards. And that's the factor theorem, which is coming up in part 2.